Okay, let's get started. Hi, I'm Mike Adams. This is my first legitimate attempt at getting through this lecture the full way. This is the Chapter 7 lecture for MET 410. And just a couple notes here. Here's the chapter outline, as you can see. Chapter outline. Oh, let me hit the draw tool. So here's the chapter outline. We are going to be covering all of this, slightly contrary to what I said in class. However, these two chapters, deflection and stiffness and critical speeds, these are an exception. You're only responsible for these two chapters for what's in the slides. So only what's in these slides. Okay, now I'm going to make a special note here, so pay attention. Special audio note. Okay, there's going to be a quiz attached to this lecture and the reading assignment. And the reason I mention that is because I'm going to be interspersing some quiz questions into the audio only. So if all you have is a printout of the lecture, you're going to be missing the audio. Now, I'm sprinkling these in such that you kind of have to watch the whole lecture or spend a whole lot of time looking for the needle in the haystack, because it's kind of required that you watch the lecture. So that's why I'm doing this. So that's the intro to the section. Please watch the full video, and some of the quiz questions that I'll ask by audio, write them down as you're going through. Please write them down, solve them later, or sometimes the answer is just plain as day. But make sure as you listen through the lecture that you write down the quiz questions. Okay, so here we start on the actual lecture material. We have shaft design considerations is right up front. Obviously, there's geometric layout. This is a physical part. Material selection is important. Clearly, stress and strength. But a special note here that you have to design for both static strength and yield and fatigue strength. So you always have to check for yield. So always, sorry, my writing here is still always check. Yeah, I'm going to undo that. Let's see. Well, I have the liberty to do this. Okay. So always, that still's kind of crappy. Let's just say check for yield. You always want to do that. And obviously, a shaft is spinning around tens or hundreds or thousands of revolutions per minute. You can imagine that gets up to 1 million or 10 million cycles pretty quickly. So that leads us into the realm of fatigue failure. So along with checking for just static yield as the shaft just sits there, you also have to check for fatigue failure. The last two bullet items, deflection and rigidity, this one, and vibration. Unfortunately, well, these are definitely shaft design considerations. Unfortunately, the book doesn't really do a good job of this. And you'll see later in the section, I actually suggest using finite element analysis for most of that. So let's go to slide 3. Okay, shaft materials, focusing in on that. There's some things that shaft materials have a big impact on and some things that it doesn't. One of the things that doesn't have a huge impact on is deflection. That's primarily controlled by the geometry. So if you have a long, thin shaft, no matter what material it is, it's going to be fairly flexible. You can stiffen it up somewhat with the material, but you're not going to get as big a bang for your buck as changing the geometry. The second bullet item, stress. This is also controlled by geometry and absolutely has nothing to do with the material. Stress is not a property inherent to the material. It's inherent to the loads that are on the part and the geometry of the part. So stress and material are totally unrelated. However, the strength of the shaft is entirely controlled by the material properties. Shafts are commonly, here's some common materials. So, low carbon, cold drawn, or hot rolled steel, that's what CD and HR, and, 1020 to 1050 steels. High alloy content doesn't really, or heat treat doesn't really benefit shaft life or yield strength that much. And we really only use surface hardening at bearing surfaces, or I would add their wear surfaces. So let's add, plus wear surfaces. Okay, and that's that slide. So we'll use, we mentioned cold drawn and hot rolled steels. So for diameters less than 3 inches, that's typically when we'll use cold drawn steel. And then for the larger sizes, we'll use hot rolled. For low production quantities, they're typically lathed, not generally the entire length at once. This is usually done in sections. And generally speaking, if you have a low production quantity, you want to minimize the amount of material that you're removing. For high production, you can form or cast your shafts. And in that case, instead of minimum material, you want minimum material removal. You want just a minimum material overall, because you might not actually be doing any post-processing to your shaft. Okay, shaft layout design considerations. Oftentimes you'll have one or more shafts coupled together. The main thing to take away from this slide is in any driveline, a driveline can consist of multiple shafts, is only have one axial bearing, load bearing. And you have to watch out for tolerance stack-ups as well as changes in temperature. So if you have 2 axial load bearings, then if the shaft grows with heat, then those 2 bearings will fight against each other and bind up. Aside from the axial layout and the supporting of axial loads, you also have to provide for torque transmission and ease of assembly and disassembly. So you notice that in figure 7.1 here, we have these stepped. This is stepped. We have a stepped shafts that we can get various components on and off, and they can stack up against each other. So you can have this gear. So you have this gear, and this might be a separate hub, right? So they would have a different diameter that they slide over. And next slide here. When we say providing for torque transmission in this slide, this can be from 2 things. This can be one shaft to another, or it can be from the shaft to a shaft component. And sometimes the shaft is transmitting the torque to the component, and sometimes, like in the case of a turbine, the component is transferring the torque to the shaft. There's several common means of doing this. Probably the most common and effective is a key and a keyway. That's the first one. There's also splines. Splines is a bit more heavy duty for high torque applications. It's sort of like a permanently locked gear on a gear. There's set screws and pins. These are kind of weaker, smaller shafts. These are weaker, more fit for smaller shafts. I'll make those notes here. Then we have press or shrink fits, so you can always press or shrink one shaft or a shaft component onto another shaft. There's tapered fits, and usually the tapered fits are drawn together with a nut. Drawn together with a nut. And then we have collets. This is an example of a collet. And a collet is a tapered cylinder. In this case, it has a split, a longitudinal split. And this is driven in between the shaft and the shaft component. So this is driven between shaft and the shaft. Oops, Control Z is what I like about this. shaft component. I've used these myself. They're common in things like small pumps. Again, this is just relying on friction, and there's usually a collet driver, or otherwise known as slide hammer, that goes has a hole in it that goes around the shaft, and you drive that collet in between the shaft and the component. As mentioned before, keys are one of the most effective and also one of the most common methods for transmitting torque. There's no particular press fit or precision fit required to get the component onto the shaft. You can use a slip fit. It locks the component into an angular orientation relative to the shaft. And you can design a key to be the weakest link, so it fails in case of a torque overload. And also not mentioned here is you can use multiple keys. For additional torque transfer. Sorry for the horrible handwriting. I'm still getting used to the touch screen. So if one key doesn't do it, you can have 2, 3, 4 keys clocked around the shaft, and that way each key carries a fraction of the torque being transmitted. Okay, shaft design for stress. We have stress. A lot of shafts are very complicated, and this is where it's important to identify the critical locations. So ID the critical locations. Sorry, I just realized that my little camera was in the top right corner. I'll fix that from now on. ID the critical locations. They're usually on the outer surface where the maximum bending moment is, where you're transmitting torque, and where there's a stress concentration. So all of these help you identify the points to look at. You could also just load your part, design your part in something like SolidWorks, and then put your constraints and your forces and your moments in, and let the computer do the work. So that's another way to identify the highest stress point. That's a bit of computer work, but for simpler shafts, you don't need to go there. You should be able to do all this on a pen and paper. But either way, no matter whether you're using pen and paper or a computer code to help you, a comprehensive load analysis is still required. And this is often purely pen and paper. You need to know what your static loads are and what your dynamic loads are. And that's something that a computer can't do for you. So this is not something a computer can do for you. When you're examining what loads are actually on a system, you actually have to think about it and draw it down on a free body diagram. Okay, now here's quiz question 3. Is if you go back one slide from here, this is a true-false question. So this is going to be quiz question 3, and it's only going to be delivered to you on audio right here. And that is, it's a true-false question. Are pins a means for transferring torque? So true or false, question 3 on the quiz. Are pins a means for transferring torque? And that's in reference to the slide just before this one. So you can back it up and take a look at that, and the answer should be pretty obvious. Here we are at slide 8. Shaft stresses. These have been customized for shafts for convenience. Generally, axial loads are ignored in this section, and axial loads are ignored because they're assuming that you paid attention to the axial layout slide and didn't add multiple axial thrust bearings, so that aside from the one axial attachment, everything else floats freely in the axial direction, and you really shouldn't have appreciable axial loads. if you've designed it right. So all this is based on the outside surface, radial load type stuff. So we're looking at alternating and mid-range stresses. This is definitions from fatigue. So it's chapter 6, fatigue terms, mid-range and alternating. Once you see mid-range and alternating, so this is obviously this is alternating, this is mid-range, this is normal stress, this is shear stress. Okay. Obviously, we're talking about doing a fatigue analysis. And if you have round shafts, there's another simplification. So we have a simplification here that you might be interested in if you have a nice round shaft. So they've already taken into account what I is, the capital I. So this makes calculation a little easier. You don't have to go looking up the second area moment, which is the letter I. Okay, so those are some basic definitions. And so here we have, what do we do with those? Well, since we have, let's go back up and see what we have. We've got raw, normal stresses and shear stresses at some point of, where are these? These are at your location of interest, right? And what we need to do for a fatigue analysis is put those into the von Mises stress definition, which is what the distortion energy theorem. So everywhere you see a DE in this chapter, that means distortion energy. Oops. Distortion energy, and that's from chapter 5. Okay, that was one of our static failure methods, but we used that static failure distortion energy used the von Mises stress. So that's why it's coming back to haunt us here. And we can plot these values on a fatigue diagram. But overall, what you're looking for on a fatigue diagram is sigma A versus sigma M. These are the values here, right here, that you would, cursor's not showing up for you, it's showing up for me. I'll have to fix that later. But sigma A and sigma M, these are the things that you're going to use to calculate or either put on a fatigue diagram or calculate whether or not you fatigued. Now, again, we have another audio quiz problem here. It's going to be problem 4 on the quiz. And I'm going to give it, again, an audio only. If you go back to the previous slide, the definition of sigma A, I would like you to calculate for quiz problem 4, sigma sub A, if K sub F equals 3, M sub A equals 2,000 pound-inches, C equals 2 inches, and I equals 1.5 inches to the fourth. So I'm going to say that again. Quiz problem 4, you're going to calculate sigma sub A with K sub F equals 3, M sub A equals 2,000 pound-inches, C equals 2 inches, and I equals 1.5 inches to the fourth. And that will be problem 4 of the quiz. Okay? So let's get to page 10. This is slide 10, shaft stresses. What do we do with that? Here's a good term here, Goodman line. We're only going to use the Goodman line. This is a fatigue analysis. So once you see Goodman, this means we're looking at fatigue. And we're only going to look at Goodman. There's a bunch of other methods in there, but we're only going to look at the Goodman line. And 1 over n is the factor of safety, or n is the factor, or the design factor of safety. And we come up with this 1 over n equals something based on our diameter and our loading. We have our loads here, our mid-range and alternating loads. So these moments, this would be bending. This would be torque. So those are moments. They're both moments, but one is a bending moment and one is a torque moment. Obviously applied in 2 different directions on the shaft. Basically, what we're trying to do with this is to determine for a given factor of safety or design factor n, what is our actual required diameter, and then generally round up to a common size. And if you're going to remove material after that, for whatever reason, round up another 16th or whatever you need to get back down to the D that you calculated. Okay, shaft stresses for a rotating shaft. We looked at, we had a bending moment and a torque. Where the bending moment comes in, if we have steady bending, so a static bending, and a static torsion. So these are both steady, means static. So you have a static bend, and then the shaft is rotating through that. That means that your bending stress, if you were to be a little particle or differential element riding along on the surface of the shaft, you would alternate between pure tension and pure compression. So that's going to give you a fatigue type of thing. Torsion is now going to be purely mid-range, unless you have something like a reciprocating engine, in which case the torque is fluctuating. For most machines that aren't reciprocating engines, you can simplify that the mid-range moment and the alternating torque are zero. That would preclude things like reciprocating engines. Obviously don't follow that last bullet. But for most shafts that are just sitting there under static conditions and rotating their way through it, M sub M and T sub A can be approximated equal to zero. So aside from the fatigue analysis that we did, so we if we go back up a couple, give me just a second, we solved for the diameter based on a fatigue calculation. So this is all solved out for you here in slide 10. This is the diameter for fatigue. Also, I'll mention that you don't have to use K sub Fs. You can use K and K sub S. They're actually more conservative. We didn't cover what K sub F and K sub Fs are. Those are for the fatigue stress concentration factors. They're not really that much different from the normal ones. They're a little lower, so I just ignore them. It's not really, it's an extra step you don't need to do. But anyhow, getting back to slide 12, regardless of whether or not your part lives under fatigue, you still have to check for yielding to make sure that you didn't yield the shaft on the first cycle. Textbook doesn't really explain this very well. It just kind of spits out a bunch of methods. It has D.E. Goodman, D.E. Gerber, D.E. Asme elliptical, and D.E. Soderberg. Nobody uses any of these ones that are underlined. At least nobody that I've ever heard of. Goodman is the only widely used criterion. If you need anything better than that, then you should be using finite element analysis. So it's either this or FEA. Unless somebody's got a real specific good reason to monkey around with Gerber, Asme elliptical, or Soderberg, there's really no reason to, this should be an R. Let me just get rid of that. Maybe it's nice that I can actually just erase or FEA. Okay. Well, Goodman, it's been around a while. It's tried. It's true. It's relatively easy. It's reasonably conservative. I can use equations 715 and 716. Let me back up a step. I'm going to switch screens here to my document camera. Here's the page where you're going to start ignoring stuff. This is page 360 and 361 in the textbook. And here we have that definition of D that I had 2 slides ago. Right here. Here's the definition of D. No, that's not it. It's this one right here. This is for Goodman. It says right here, modified Goodman. And then right here is D. This is the D that's in the slide. This is the only D you're going to use. Then they redo all this for Gerber, and nobody does that. So you're going to ignore that. And then they do it for Asme elliptical. No, nobody does that I know of either. And Soderberg. So all of this on page 361, this is to be ignored. This is to be ignored. This is the only one on page 360 that we're interested in. The stuff corresponding to here, as you can see, the word Goodman. If you see anything else, D.E. Goodman is good. So this is still valid. Sorry, I'm just kind of looking at two different places. This says Goodman, so this is good. Gerber, no good. X. Elliptical, no. X. Soderbergh, no. We're not going to do that. Okay? So that ought to make things a little bit easier for you to concentrate on that. And, you know, here's what all these things look like on the right-hand side of a fatigue diagram. And, you know, this is the only one that we're interested in, right there, modified Goodman. Everything else gets a big fat X on it. Equations 7, 15, and 16, eventually to check for yielding. So this is, you know, we already did our fatigue analysis before, so now this is a check for yielding. And again, we're going to use the von Mises stress again. And I just turned the page in the book, and here it is. It's actually right here. This is 715 and 7. So 715 calculates sigma max prime. That's the maximum combined stress of mid-range and alternating that you could possibly see. And that obviously needs to be less than the yield strength. And then here's your factor of safety based on that is 716. That's your yield factor of safety, n sub y. Let me zoom in on that a little bit. Super fancy guy here. So we're going to zoom in a little bit. And here we have sigma max prime. I know it's not that clear because the camera's actually kind of far away, but this sigma max prime here needs to be in 715, needs to be less than your yield strength, obviously, but then you can calculate your factor of safety in 716. However, you notice this note underneath that there's a quick conservative check, and that is that sigma max is just sigma a prime plus sigma m prime, and that'll always give you a conservative estimate. So I love the touch screen here. So this last note right here at the bottom, well, actually, I don't really have a pointer here, but maybe it's showing up. Yeah, here it is. This last note right here, this is a quick conservative check where sigma max prime is simply sigma a prime plus sigma m prime, and that'll always give you a conservative estimate, and it's a lot simpler than equation 715. And this is all, again, a check for yielding, okay? All right, so we can dispense with that slide. This gets us into example 7.1, which is, you know, just previously shown on the document camera. There's a lot of unnecessary and confusing information in this. These are my own notes, right? So check. Unnecessary and confusing, yes. So let's walk through it and cut through the mumbo jumbo. First of all, what is it asking for? It's saying that a machine shaft shoulder that has basically a step in the shaft going from a diameter of 1.1 to 1.65 inches with a fillet of 0.11. They give you a bending moment, a static bending moment, and a static torsion. And they give you the ultimate strength and the yield strength, and they have what's the fatigue factor of safety and what's the yield factor of safety. That's basically what this is about. So they go through, and the first thing they calculate is K sub F and K sub Fs. You're not going to do that. Nope. Just use K sub T and K sub Ts. So these K sub T you can get from this figure right here, and K sub Ts you can get from here. We don't care about this, and we don't care about Q shear. K sub T is always going to be greater than K sub F, and K sub Ts is always going to be greater than K sub Fs. So just use K sub T and K sub Ts. It's conservative to do that. So, well, actually, I already have conservatively right there. So I'm just going to underline it. You can conservatively use K sub T and K sub Ts. It's less calculation, and there's really not that much difference when it boils down to it. Okay. Then they go through. These are the fatigue life modification factors. So these are the modification factors. Can't forget about those. And then they finally calculate the endurance strength, and they get 29.3 KSI. Now let's go up a page and notice that the actual yield strength is 82 kpsi, but our endurance strength is, our endurance limit for infinite life here is 29.3 kpsi. That's quite a difference. It's almost 1/3 of your yield strength. So definitely this illustrates how you want to certainly keep track of whether or not your part has potential for fatigue, but always for shafts we're interested in that. Okay, they gave you the static moment. So why is the static moment turning up as an alternating moment? Well, as I explained previously, it's because a spot on the shaft, as it rotates through that static bend, rotates through the compression and the tension, back to the compression and back to the tension, over and over and over again. And as a result, it sees a purely alternating tension and compression. So that is definitely a alternating bending moment. Okay. Then the torque is just a steady torque along the axis of the shaft, and they've approximated this for around, for this non-reciprocating engine shaft. And now you can apply the equation 7.7 and solve for n. And this is the only thing that we're looking for right here. All this stuff is garbage. Nobody ever does that I know of. So this would be the end of that part. This would be your fatigue design factor that we were looking for. If we go up a couple slides right here, that's our fatigue factor of safety. And if we go back to slide 15, there it is. Boom. N equals 1.63. That's our fatigue factor of safety, according to Goodman. That's the only one that counts. Okay. Now we have to check for yielding. So we're going to look at equations 715 and 716. So this is equation 715. This is equation 716. And as we see, plugging in all the numbers that we have so far, we get a yielding factor of safety of 4.5. This part right here corresponds to the quick note at page 362, right above example 7.1. This is the quick and dirty method that's described in the last sentence in the body text on page 362, and you can see that it is indeed conservative. So it's a quick conservative estimate. Sometimes that's all you need, just to say, well, this is the design we're going with. Does it yield or doesn't it yield? And what's a conservative factor of safety? So if you use that quick note, it kind of saves you a little bit of time, and it'll oftentimes give you the answer that you need anyhow. Okay, so estimating stress concentrations. This is, again, something that eventually you will want to do with finite element analysis, and just let the program itself do its thing and tell you where the maximum stresses are based on the design and fillets and undercuts and everything else that you've designed in. But usually you're going to have a problem with a shaft. If it's going to fail, it's going to fail somewhere near a stress concentration. So you're going to definitely have to pay attention to those. But when you're first getting started for the design, so this is an initial design. You don't want to use an estimate in a final design stage. But then again, you don't want to have to recalculate very complicated stress concentrations over and over again using whatever formula or tables in the back of the book. So as a result, they've come up with kind of an estimate chart, and that's given in table 7.1. So if you're just kind of going to eyeball something during the initial design, you can estimate the stress concentrations using table 7.1. Don't use these for the final actual part. That's important. So once you actually have the part almost fully designed or fully designed, then you actually have to go back and detail calculate the the stress concentration factors. Okay? So now, so one way to reduce stress concentration at a shoulder fillet, these step changes in shaft diameter are quite common. Usually it's to seat a bearing or some other shaft component. And there's 3 different techniques given here, but these aren't the only ones. But usually you have some sharp corner here on a shaft component. So this is sharp. And you really don't want a sharp corner at a step in the shaft. So, so even though the bearing has a sharp corner, you don't want to have an even sharper corner to match that on the shaft. So these are some methods for undercutting or removing material or providing a more generous transition. Now, I'm going to have quiz problem number 5 now, and it's off of the previous slide. So if we were to look at this slide real quick and then come back down here, I'm going to give you an audio quiz problem number 6. And this is, the question is for I'm sorry, quiz problem number 5. Sorry, strike that. Quiz problem number 5. What is the approximate stress concentration factor for a retaining ring groove under torsional load? So let me repeat that. On the previous slide from this one, what is the, on that table 7-1, what is the approximate stress concentration factor for a retaining ring groove under torsional load? That's quiz problem number 5. Make sure you write it down, figure it out later. Let's get on with the lecture here. Okay, deflection considerations. This is really a complicated issue. You usually have a stepped shaft, multiple loadings. This gets complicated in a hurry. And, but there are some guidelines. So I would do the deflection analysis. Hang on a second here. You can't do all of this with a computer, but you can do your deflection analysis. Oops, sorry about that. You can do your deflection analysis using FEA, but you need to know what are some limits, right? What are the limits for what you find? So your FEA code can give you what your deflections are, but it can't tell you what are the reasonable limits of deflection. And deflection includes lateral deflection and also angular deflection. Okay, so here are some typical ranges for slopes and transverse deflections. So this is a particularly, so once you use an FEA code to calculate for you what your actual slopes and deflections are on your shaft design based on your static loads, then you can compare that to sort of the allowable ranges on table 7.2 for gears and bearings in particular. So gears and bearings are particularly sensitive to deflection and angular deflection and transverse deflection. Gears can either get mashed too tight together or come out of mesh, slightly out of mesh. Ball bearings, roller bearings, they don't like to be edge loaded, particularly roller bearings, so they can only tolerate really a certain amount of angularity or slope of the shaft. So this one is particularly useful, table 7.2, once you get your finite element data or computations done. So if we wanted to do deflection considerations by hand, it's really straightforward. It uses, you would use chapters 3 and 4, but it's really, really tedious. It's not, it's like it says here, straightforward but tedious. And then, each point of interest requires an entirely new deflection analysis, so you have to iterate. And as a result, there's a lot of, even though it's a simple process, though tedious, there's a lot of avenue. It's a lot of work, and there's a lot of avenue to introduce error. Once you have 10 or 20 pages of handwritten analysis, almost a guarantee that there's an error in there somewhere. You're going to have to figure out, even under the best of circumstances. So usually this is done with the assistance of software. In this modern age, almost nobody goes through this by hand anymore. You still need to know the hand calculations to double check certain aspects. Make sure that your software is not putting out garbage. Make sure that your inputs to your software are okay, and to always check your calculated software results with a quick and dirty hand calculation. And really, the workhorse tool for this is finite element analysis, and SolidWorks simulation would be one example of that. Not the best, but suitable for most applications. But there's certainly better FEA packages out there. So other than the as this last bullet says, this is one of those things, deflection. Other than this and the previous slide, this section can be ignored, and I strongly urge you to use finite element software for this task. Right? Boom, right there. That's what it was built for, so that engineers don't have to do this kind of stuff by hand like they used to. Okay? So that brings us to slide 23. Critical speeds for shafts. This is extremely important. If you hit a critical speed and stay there, that's critical speed is essentially a natural frequency. So if you stay at a natural frequency for too long, you will potentially blow the shaft to pieces. Catastrophic failure. That's what happens. Clearly, it's important to know what your critical speeds are, so that you avoid running your shaft at that critical speed. So you want to avoid running your shaft near a critical speed. It's a natural frequency. You're exciting it with the max eccentricity that's going around at that same matching frequency. And generally that does not lead to good things. It leads to either early fatigue failure or yielding or machine total destruction and annihilation. And as important as this is, unfortunately the textbook right here gives a completely, it's entirely incomplete and relatively useless, right there, treatment of this. They use some really outdated methods that haven't been used since 1980, and even then, a lot of information in this section is not even up to 1955 design standards. Trust me. The folks who designed the first jet engines, just at the end of World War II, we're using things that are more advanced than what's in this textbook section. So this is really for something that's so important. It's so poorly treated in the book. So again, except for this slide, you can ignore this section. And if you ever have to do this, use FEA. That's my two pieces of advice there. And we can skip to the next slide. We're going to move to the next section, which is miscellaneous shaft components. This section actually has some really useful and practical information, particularly in the design tables. Whoops, bad line. I'm still getting used to the touch screen, so bear with me. So particularly the design tables. And there's more shaft components that are here. To me, a shaft component could be a series of like a bladed section, a pump impeller, a motor winding. There's all sorts of components that could be a shaft component. For some reason, they've kind of focused in on attachment and torque transmission components. So this is a subset of shaft components. Which is kind of a shame, because this is again this would have been an opportunity for the people who wrote this book to really let you know what kind of things are mounted to shafts. These are kind of the things that attach shafts or components together. So this is kind of the connecting points, and it's not even a complete list of connectors. I can see why they would concentrate on keys, and but the rest of it's just kind of incomplete, but it's still useful for these three things. All right, so set screws, I've used these a lot in shaft design, and what you do is you if this is your component and this is your shaft, you would drill a threaded hole here, and you would screw the set screw down into that hole, and the end of the set screw, so the set screw would go in here. Whoops. Set screw. I kind of sort of squeezed that in there here. I just realized I'm running into the camera here. Control Y. Your set screw would get screwed down into the shaft component, and then the tip of the set screw would push up against the shaft. Mostly what I've used I've used a softer material to avoid damaging the shaft. The shaft, again, could have a fatigue failure scenario, so the last thing you want to do is put a scratch on the surface. So these tips can be, I've used a lot of nylon and brass. So nylon is common, or brass as well. Those are, I think, the two most common soft tip set screws. Lets you really tighten them down without marking up the shaft. This harder material to provide a slight penetration. I've never seen anybody want to do that to a shaft. Nobody ever wants to dig in and make a permanent divot in their shaft, because when you do that, if you do this component doesn't come off easily. When you dig into the shaft, you raise up material on either side, and now you have a slight interference fit there, and now it's not so easy. Now you got to pound the hell out of that shaft component to get it off the shaft. So they have this in here, but I would not recommend that you do that unless you have a really good reason to. It introduces scratches to the shaft, which can decrease your fatigue strength, and it makes dismounting the shaft component that much more difficult. Next slide. This is pretty good for the standard sizes and what their holding power is if properly torqued. So they give you the torque here. If you're going to need a torque wrench, and then you know what the holding power is. And if you take the holding power times the radius, you can get a torque. So that this force times radius equals the torque that you can transmit. Whoops, and I put that underneath my ugly mug again. So if this is your holding force, you can say that your torque transmissibility is F times R, where R is the radius of the shaft. And of course you need a torque wrench here to do that, to get your proper seating torque. This gives you an idea of some of the sizes down here and what kind of torques they require to be seated properly. And these aren't very heavy-duty seating forces, and particularly when you put in representative radii, you'll see that set screws really don't transmit a whole lot of torque at all. So I've only seen these in small, like laboratory test setups or small shafts. You certainly, even 1 inch, this is getting into territory. I would say you want to keep this under 1/2 inch. I wouldn't, if you have anything bigger than a 1/2 inch shaft, I wouldn't use a set screw. Otherwise, if you need a 1 inch shaft, that means you're transmitting torques through a 1 inch shaft, and these torques just aren't going to cut it for a 1 inch shaft. All right. And this already has a design factor in it. Let's see here. Other than that, we have keys or pins. This is going to be the most common. Just the square key with, and if we were to extend this key has a length. Right, let me undo that. Let me make it a little shorter. Okay, so the key will have a length, prescribed length. Here's an important note about this. These rectangular keys is the actual cross section. So the cross section is determined by the shaft diameter. This is determined by the geometry, specifically the shaft diameter, but the length is determined by the torque requirement. So the more torque you need, the longer of a keyway you need, and if you max out on your key length, then you need to add a second key. Usually you clock at 90 degrees from the first key. So that's all these other keys. I have to say I've never actually seen any of these other keys, but you know, hey, the square rectangular key that's given right here, that's the most common. Tapered pins, I've seen these in some mechanisms, but not used with shafts. I know they're probably used, but if you're going to use one, God knows what you'd use it for locating a component onto the shaft. I don't really suggest it, but if you do, here's again some standard sizes. And here we're back to keys with standard sizes of keys. This is actually really useful, so that you know what width and height. So as I said before, if you're it goes by shaft diameter, and there's a range here. You know, here's the range. So so we have a. I'm going to undo all that. So if you want to size a key and the keyway depth, so these are the two things we're trying to do. We're trying to determine what cross section of. So this is the cross section here. Cross section, and of course then the keyway depth. So that's not the length. So basically your keyway cross section, your width and height, is based on the shaft diameters, and these are the shaft diameters. And you can see it's over 5/16 to include 7/16 is the first one, right? There's a range, and within that range you would use this cross section and this depth, and then you would calculate what torque you want to transmit to get the length. That's how it works with the key, and that's about it. So this is actually a really useful table. This is really useful. Without a table like this, you'd actually have to try to either eyeball it or calculate it, figure out, well, what size would not give me too big of a stress concentration and all that sort of stuff. They've kind of already done that for you. It's standardized. You just look it up off a design table like this. Keys generally fail by direct shear or bearing stress. Bearing stress means two surfaces pushing against each other. I would say this is the more common. If you see one that's all mushed, so this would be if you see one that's mushed, that's probably this. If it just broke clean, then it's probably direct shear. It's a clean break. And this is what I've been mentioning. You can design the key length to only provide so much torque transfer, and beyond that the key will fail. So in this way the key becomes the inexpensive weak link, and this is one nice thing about keys, is you can design it so that if you over torque that the key fails and the shaft doesn't fail. So you want the key to fail. Key fails. Whoops. Before the shaft. Trust me, the shaft is going to be orders of magnitude more expensive to replace than a stupid key, a 50-cent key, right? So you know the shaft might be $100,000, $100,000, $1 million, whatever. Believe it or not, there's shafts that cost millions of dollars, and the key costs 5 cents to $50, depending on if it's a huge key, right? So you definitely want design the key to fail before the shaft. The key length might be limited, and they give you some guidelines for that on avoiding getting too close to the too long of a key based on the shaft diameter, and how to place additional keys 90 degrees from each other here. And typically key stock is readily available, and if you need to, you can set screw that sucker in to place it, but that's not always necessary. Sometimes these things have a fit to fit, so you actually have to tap the key in, and they're usually held pretty securely. but you certainly don't want the key to go flying off the shaft once it starts rotating. Okay, now if we go back 2 slides from here, we had a chart. Here it is, keys, and we're going to use that for the quiz problem number 6. So this is an audible question that 2 slides back. Here's the question. It's going to be a numerical answer. It doesn't matter what significant figures. Just put it in decimal with however many 2 or 3. It doesn't matter. For a 1-inch diameter shaft, what should the keyway depth be? So here's question 6 on the quiz. For a 1-inch diameter shaft, what should the keyway depth be? Write that down. Make sure you write it down. It's off this table that 2 slides ago. And again, question number 6. For a 1-inch diameter shaft, what should the keyway depth be? And you can look on that previous figure from 2 slides ago, and that'll tell you what you need to know. Gibhead key, I just have this up here as a dummy slide to give an audible piece of quiz material. Again, I've never actually seen this done, but I would imagine that it is. So this takes the place of a collet. Remember collets? So usually it's cheaper to use a collet. So that's why I've never seen these. You know, you have to broach this or machine that in somehow. The nice thing about a collet is you finish up the shaft, you finish up the ID of the hub, and you grind a 105 collets or 10,000 collets. You pick a standard collet, and you just drive the collet in there, and you don't need a groove. If you need any more torque transmission than a collet can handle, then maybe a Gibhead key isn't actually the best answer. Maybe you need to go to a spline or something like that. So I've never actually seen anything like this. I've seen heads like this, but I've never actually seen a tapered key like this. I'm sure they're out there, but there's other better, cheaper methods for doing that. Woodruff key, never seen this. Not even sure if I know what it looks like from this picture. You can completely ignore that. I have no idea what that is. Stress concentration factors for keys. This is pretty useful to give you so you don't have to look up. So you don't. So if I ask you, hey, what's the key seat with a ratio of R over D 0.02 Peters bending stress concentration factor for this keyway? If you've actually listened to this lecture, you should know that you don't actually need to go to the table A15 or whatever in the back of the book. That these things are given, and for approximation, and that you can just use these numbers as the value as long as you're staying to the standard keyways that were given in the chart where the quiz was attached to. Quiz question 6. So, and this is the other thing, you want to keep the key seat at least 1/10 of a diameter from a shoulder fillet, because you don't want 2 stress concentrations combining. That's the last note on that one. I'm going to take a brief break here to just, I think I have I'm on slide 34 now, and I'm going to go to slide 56. So I'm going to make sure that I actually recorded half the lecture here, and I'm going to stop recording, and then there will be a part 2 to this lecture with additional quiz problems embedded. Okay, so make sure you check back for part 2.